Okay, so what we're going to do today, we're going to finish up cloud networks and make a little dent in transactions so we have a shortish day Monday. That'll be it. Okay, so cloud networks, where we left off, we had talked about service-oriented architecture, modularity, all that good stuff. So we're going to zip ahead here. Let's see. Okay, yeah, so where we ended off was here. We talked about how once an organization implements service-oriented architecture as its standard way of designing applications, it gets a lot easier to deploy them to the cloud because it doesn't really matter where the pieces are deployed, they can still interact with each other. So the cloud then has the freedom to deploy the application components wherever it can optimize performance. All right, and there are other benefits too, that it makes it easier to scale things, it makes it easier to reuse components already in the cloud, that sort of good stuff. Okay. Now, another thing cloud uses, virtualization. So we talked about one part of it is the ability to flexibly deploy application components. Well, part of that in a bigger picture is virtualization. Virtualization is where you're making a copy of something that fulfills the same role, does the same functions, but is deployed differently. And when we talk about virtualization, we often talk about hardware virtualization. So the idea that instead of renting a particular server, you actually have the functions that that server performs distributed over multiple pieces of hardware. Okay, so for example, let's put this in Paint. Suppose you, as a customer, wanted to rent one particular machine, right? A copy of a desktop, and you on that desktop, maybe you're running the whole Microsoft Office suite. You know, I'm going to make a different thing down here that I can reuse. It's a little easier. Okay, so there's PowerPoint and Excel and Word, and what else shall we tack on as a last one? I don't know. Maybe this can be Access. I don't know. Okay, so you have this set of Microsoft applications that you're using, and one thing you could do is simply deploy them on a whole bunch of servers, right? So you could rent out the specific servers and say, okay, worker number one, you get this machine, worker number two, you get this machine, worker number three, you get this machine, and so on, right? This would not be virtual. This would be, you actually rent out specific machines, or, you know, within the scope of a big machine, right? Something like this, you actually, like if it's a multi-core server machine, for example, you might basically run all that stuff on one server. But it wouldn't really be virtualization. For true virtualization, what you would want to do is have several servers, and each one of those servers runs a specific application. For example, if you're using Access, you connect to the machine that's using Access. If you're using PowerPoint, you connect to the machine that's using PowerPoint. If you're using Excel, you connect to the machine that's using Excel. The nice thing about this is that if you need to have multiple copies of Excel, you could scale them separately. So for example, if you need to run, you know, let's say your application mix at any given time is, say, 100 copies of Access and 200 copies of PowerPoint and 2,000 copies of Excel, and I don't know, say 500 copies of Word. Okay, if you were going to try to do that without virtualization, you would have to go with this one. You would need 2,000 machines, and every one of them would have to run this full Microsoft Office suite. However, right, with virtualization, you don't. You just need enough machines that can run all of these. So for example, if you can say run, let's say it's really, really weak and you can run like 100 copies per server. Right? We'll keep the math simple. Then you need one server, right? You need one server for Access, and 2 and 20 for Excel, and 5 for Word equals what? 28 machines, because you can bundle them up together like that. So that's essentially the power of virtualization. It allows you to break apart these hardware functions and reallocate them to different machines so you can do it much more efficiently. Basically, you need less hardware to perform the same set of tasks. Okay. So all this, cloud operations need latitude to assign traffic and connections to manage quality of service. Okay, this is basically the same use of capacity and prioritization, except it's on a bigger scale. So it's applied to all of the users, not just to one. So it doesn't matter who the users are, if the cloud service needs to deploy, say, 10,000 copies of Excel, it can run all those on, however many servers it requires. It doesn't need to run those 10,000 Excel copies on 10,000 separate machines. Now, this is a wonderful thing because, first of all, once quality of service is good, users tend to not really care what server their work is on. And in any event, most couldn't make an informed decision anyway. So that they just say, you know what, cloud, put the stuff wherever it needs to go, you handle it, and then that's one less thing I've got to worry about. Now, factors affecting quality of service. Well, one, physical proximity. Anytime the cloud service, the physical machines are closer to the end users, it's going to be a little bit faster because the electrons, the signals, they don't teleport through the cables. So the typical number there is about 1 millisecond per 100 miles. So if something's on the other side of the world, you're talking about a 1/10 of a second delay. Server load and reliability. So if the servers are busy, if there's a lot of users on them, or if the users are doing a lot of stuff, yeah, things are going to slow down a little bit. Others, occasionally you see reliability issues. Sometimes servers fail, although it's becoming less and less of an issue over time. On occasion, you'll see system-wide capacity issues. It's rare, but it does happen. For example, on Amazon Prime Day, you might find that your Amazon Web Services stuff is a little bit slower than usual. Other things, inefficient applications. So one of the big things that people don't always realize when they're deploying stuff to the cloud is basically these sort of modularity issues. So you might think, let's say this, you might think that your system is well designed because it runs well under your own roof, right? If it's under your stuff, maybe it runs really well, and maybe that's because it's all running in RAM, okay, on one machine, right? So there aren't, strictly speaking, any dependencies built in, but just the fact that you have these pair of applications, right, or this pair of database tables, whatever you're doing, it's on the same machine and it's all in RAM. So any communications back and forth between them are going to be at super fast RAM speeds. And you just haven't really thought about that. And when your system gets bigger, and spreads across multiple pieces of hardware, or well, let's hello. I'm gonna mute people. That's okay. Let's see. Can I mute people? Who am I gonna mute? I don't have access to that at the moment. There we go. All right, we're all good. When your system gets bigger and spreads across multiple pieces of hardware or gets deployed as separate modules, then these many intercommunications between applications can slow things down. Okay, so this is the kind of problem that happens. You have a system, worked great under your own roof, but even though you think it's well designed because it works well for you, when you put it to this new environment, yeah, all of a sudden, nope, doesn't work well anymore. There's too many of these intercommunications built in, everything's slower. You have to go back into your application and say, oh yeah, we got to redesign this thing to work better in the cloud. That often happens. Okay, and of course, as the number of users goes up, yeah, you can have issues with that, especially if your cloud contract has reserved a specific number of machines rather than flexibly expanding with demand. All right. Now, most businesses, when they go to the cloud, the big thing they think about is they're going to save money, or at least that was the big thing 10 years ago. Nowadays, one of the important things is also the ability to do things more quickly, so agility. Good example of that Intuit, I recently put together a case study on them. So Intuit, you know, they do TurboTax, they do all this tax software stuff. One of the issues they have is they have a very, very cyclical business. So they get a lot of, for their TurboTax, for example, they get a lot of traffic ahead of the annual tax, you know, tax deadline, and for businesses ahead of the various quarterly deadlines. So they get a lot of traffic there, but not a lot of traffic the rest of the time. So they wanted to shift to cloud to take advantage of some of those, so they wouldn't have a lot of hardware gathering dust around the year. They wanted to take advantage of that sort of virtualization where they could pay for what they need when they need it. Now, the other thing they found out though when they shifted to cloud, it was much easier to integrate their applications with other applications. So when they put it to the cloud, they needed to redesign some of their applications to work more in a modular way. Right, so they did this service-oriented architecture. They deployed their various applications as modules. And then one of the new features they wanted to implement was something called a chatbot, which you've surely heard of. Well, if they had not had their software being modular, it could have taken years to get that all integrated. But because they already had their applications designed as modular applications, they were able to pick and choose from one of the available chatbot services out there. They integrated that. Basically what they had to do was link the chatbot vocabulary with the specific topics in their system. They'd gotten all that up and running within a couple months. I mean, it was ready to roll out in a couple months. Whereas again, if they'd had to do that on their own without the ability to pull a service from somewhere, it could have taken years. So that's what I mean when I say agility. Once you've designed your system with the service-oriented architecture in place, it becomes much, much easier to integrate new features from other applications into it. Okay, now, as far as data, one of the things that we see with relational databases is they're typically built around the same kind of tables, storing the same kind of data. So for example, you might have a table of customer invoices or customer records that basically they're all going to be pretty much the same. There's going to be some variability, you know, some customer names will be longer than others. There'll be some dead space in the database, but it's close enough, you can live with it. But if you're doing other kinds of data, for example, if you have data of videos or images or documents, those don't get processed well in an ordinary relational database because the size of them varies so much. So if you wanted to have a field allocated that had to be a fixed size for every record, you'd have to allot the largest possible size of anything you see in the database to hold it. And that's a hassle. So one way you can get around that is you can segment the things, but that's a lot of work and it's not something you're going to get in off-the-shelf software. Another problem you often see with relational databases is when they get too big, you get back to this same problem, right? So this is a similar thing that happens when relational databases get very large. The process of multi-table queries also gets slow. And for the same reason. So for every record in one table, you have to cross-check and look for another record in another table. And if the tables are so big that this isn't getting processed in RAM, it's being stored on multiple machines, again, your operations start happening at network speeds in terms of milliseconds instead of RAM speeds at microseconds. And suddenly, boom, you cross that threshold and everything's a lot slower. What do we have here? Good morning. Oh, yes, good morning to you. Thank you. All right. Look at that, more people. And more chat. The exam is on Wednesday of finals week. Okay, very good. Yeah. Okay. Anyway, so one of the things organizations might do is they shift to what are called NoSQL databases. So not your standard relational databases. And basically those make it easier to run these, they make it easier to retrieve data. What they tend to give up though is the ability to process multi-table queries. One thing I'll add here was say, can add data without predefined schema, easily change schemas. The schema of a database is basically the way the table is set up. So what fields it holds, the format of those tables, the structure of the table. In an ordinary relational database, that's going to be fixed. Every record in the database is going to follow those same rules. In a NoSQL database, you can cut some of those corners. And in an extreme case, you can have what's called a key value store, where you still have a key to uniquely identify each record, but then the value can basically be any data structure you want. So it's like, so a key value store in a way is like a table of tables. Every record inside a key value store can have a unique data structure. And again, one of the things with relational databases, if they're searching for running a query on a table, for example, and they're looking for a couple particular fields in each record, they know exactly where those fields are. They know that every record's going to have them. They know what the offset is going to be on all of them. So it can get processed pretty quickly. On the other hand, in a NoSQL database, you're not going to know that. You're going to have to look at every record to see if the fields are even there. You don't know where the fields are going to be. And so it's going to be a lot slower. There's quite a bit more processing involved. So one of the things there, you can do multi-table queries in a NoSQL database. It just tends to be much slower than happens in relational databases. So typically where you would implement NoSQL databases is in situations where you wouldn't need to do queries across tables. For example, like Facebook photos, right? There's a reason why you don't have a lot of ability to search through photos. You can't just run a query on Facebook that says, show me all the photos from people in Chicago that were posted in October. Right? There's going to be a lot of cross-table stuff going on there, and it's going to be too much work for Facebook, especially considering the size of their database. That's why that's not a feature. It's just too much work. Okay, another feature, auto sharding. With NoSQL databases, you can split up tables across pieces of hardware, and it works a lot smoother than it would for relational databases. Again, because what you're going to use NoSQL databases for. So a relational database, the whole point of having it is that you can do tables involving multiple queries. And because you want those to happen reasonably quick, you're going to try to avoid splitting tables across pieces of hardware. NoSQL databases, because you're typically not doing you're not doing queries involving multiple tables, you're less worried about that. So it's pretty easy to say, this table got too big, let's split it off to another piece of hardware. Okay. So again, practical example, suppose you have a big table of customer purchase data, right? And if you had a relational database, every record in that database is going to contain the same amount of data, not too much empty space. So there'll be a name, there'll be an address, there'll be a list of invoices that the customer has bought from. Yeah, that's about the sort of stuff you have. Now, problem happens, some purchases are going to be for many items, and the database system needs to accommodate them, right? So some invoices might be one item, some of them might be 100. If you force this strict relational setup, you're going to end up with a lot of empty space in your database. Another thing, if you want your database queries to run quickly, you're going to need to optimize it in some way. You're going to have to decide what's going to be located where and how that data is going to be distributed over your hard disks or over different parts of your system. And if you change the schema, if you change the setup of that database, then suddenly your carefully calibrated system, that calibration will be broken and you'll need to recalibrate it. So it's easy to go into your database and say, this field is going to have a new format, but then you have to apply it to your whole system. And that's going to take a while. Just the fact of updating all the fields and relocating everything on your hard disks, that's going to take a while. And then calibrating it to work well, that's going to take some more time on top of that. And again, this is for a fairly simple thing like customer purchase data. If you try to do it with more complex or difficult data types like image or video libraries, documents of various kinds, yeah, it's going to be even more of a headache. Anyway, if you're interested, there's some links throughout, like this one, blog article, NoSQL databases. What we're tending to see lately is a little bit of merging between the two. So 20 years ago, you basically just had relational databases. About, 10 years ago, NoSQL databases started getting a lot of attention. They're still used in various places, right? Again, Facebook's system for images is basically a NoSQL database, and they have some others. But what we're seeing is businesses don't want to entirely get away from these relational databases. What they want to do is be able to do the things they need to do more quickly. So they'll put various tweaks. They'll cut some corners on it, for example. Like one of the things that Google does is it set up its page indexes. So anytime it does a batch of page updates, like it goes and sends its spiders out to review pages, grabs that data and updates its database with it, it wants to do that in a fairly small cluster. It doesn't want to have to put the entire database on hold while it updates a small subset of pages. So they've optimized their system to do that. It's basically a relational database, but in a way the database is broken up into segments and they can process those individual segments separately. So businesses have found various ways to kind of go between these two. They're not all the way at the extreme of a NoSQL database, but they find the relational database too limiting. So they're in that kind of middle ground nowadays, a lot of them, a lot of the big ones. Okay. Now migrating to the cloud. So businesses, when they need to migrate to the cloud, they have to decide what they're going to migrate to the cloud. So basic question, data, applications are both. Are they going to keep their data and just run the applications in the cloud? Are they going to keep the applications and just store the data in the cloud? Or are they just going to send everything up there and make it somebody else's problem? And the other question is whether any downtime is acceptable or not. So some years ago, typically a business would basically have to put its operations on hold for a little while it sent everything to the cloud. And that was kind of a headache. They didn't want to do that. That was one of the limiting things. So they started bringing in these technologies where businesses could keep everything running under their roof. At the same time, they were starting to feed data to the cloud. And essentially, after a day or a few days, they migrated all their relevant data to the cloud. They could run their system up there, and then they just start injecting all the new data into the cloud, and they pull the plug on their old system. So there's technologies to do that now. So usually downtime isn't a problem, at least not with the major cloud services. Anyway, so reasons why you might do some of these. So if you want to send only the data but no applications, if you have a really critical application that you don't want to take offline or you don't want to risk taking to the cloud, yeah, okay. You know, you keep that under your roof. You just send the data. But of course, you need a fair amount of bandwidth to continuously update the data in the cloud. For that, they have some services. One thing, Amazon has a set, like you can look at Snowball, Snowmobile, some of these other ones. Okay, so Snowball Service Cloud. Snowball is basically a little case, you know, think of it like a suitcase that carries some sort of data storage device, like a petabyte of data. Okay, the other ones, the bigger ones, so Snowball, again, is like a petabyte hard drive. Snowmobile, if we do that, that's where they basically drive a truck up to your house, right, up to your business, that can carry 100 or so of those snowballs. Boom, exabyte scale data transfer. So exabytes are a lot of data. 100 petabytes per snowmobile. So basically they send a 45-foot long shipping container up to your business. You load it up with all your data. They cart it over to Amazon, and on some high-speed direct connections, they just hook those things up and they store it in Amazon's cloud. If you want to, you can get a chain of like 10 of those, which makes it exabyte data transfer, right? 1,000 petabytes is an exabyte, and an exabyte is a colossally huge amount of data. Okay. Another possibility is machine replication. So machine replication, you try to duplicate exactly what you have under your roof in the cloud. So typically you're going to move the entire application stack, all the applications you're running, you're going to migrate them to the cloud. And there might be some downtime with that. But again, this is less of an issue these days. The advantage of machine replication is the configuration that you have in the cloud is going to be pretty similar to what you have under your own roof. So there's not going to be quite as much testing involved. I mean, sure, you got to test it, make sure it all works correctly, because there are all these virtualization, modularity issues, things like that. But because you're trying to do it in you're trying to, as far as you can, to set it up the same way in the cloud as it's set up on your premises, there's not going to be quite as much testing that you need to do. The other one, physical to virtual, that's where you have all your applications deployed as services, as modules. You deploy those modules to the cloud, and you give the cloud latitude to deploy them on any machines that's convenient to maintain quality of service. So conceptually, it's pretty simple. You're just going to give the cloud everything you have, your applications, your data, and you're going to tell them, make it work as best you can. Now, this process, again, it's automated, so it's not you know, if you're a big business and you have a lot of data, yeah, there's still going to be some stuff you got to do. But if you're a fairly small operation, it's relatively painless. But generally, you're going to have to do a lot of testing to make sure that things work in the cloud the same way as you thought they would. What typically happens is there might be some sort of constraints or dependencies in your system that you haven't really thought about. And one of those is just maybe the way your system is designed, the machines are close to each other, or you have different applications running on the same machine, sharing RAM, and they run a lot faster that way. When it gets broken apart into separate machines, suddenly it slows down a lot. So once you get those things out of the way and that everything works the way it's supposed to, then yeah, it's fine. Last one, disaster recovery. So for disaster recovery, you basically build a redundant copy of everything you have in the cloud, and for recovery purposes only. So you still keep everything running under your roof, right? Data and applications, both of them, but you make a copy of everything in the cloud in case something like an earthquake or a fire hits some of your facilities, so you don't lose all your data. All right, and those are the big strategies. Those are reasons why businesses do what they do. Okay. Amazon Web Services. So Amazon, we've said before, is the biggest of the public cloud providers. Typical things that businesses might want to do. Number one, they might want to rehost their application. So keep the application the same way it is, but they want to deploy it differently so they get better performance at scale. Another one is replatforming. If they want to move it with some changes, for example, there's a new database system they want to integrate it with. And again, this is typically done either to improve performance or in some cases to make management simpler. So you keep the application mostly the way it is, but you put it on a different platform and you integrate it with different other applications. Repurchasing. So if you want to keep the data, but you want to change the application, that's an obvious one. And then last, sometimes you have to rebuild the entire application, and you want to do that before you deploy it to the cloud in the first place. So Amazon has some of these automated migration tools. Oh, we got people. So typically the business will keep all of its originals operating while it's doing the migration process. Again, we have some of these high-speed data transfers. So Snowball, Snowmobile, if you have 100 petabytes, that's going to take a really long time to send over a standard internet connection. So you probably don't want to do that. It's probably going to be a lot faster to just tell Amazon to send over the truck and you load up that stuff. They also have Firehose. I'm sure by now they have additional ones for streaming data. So again, this is the application. If you have a lot of data that you need to continuously send to Amazon at the same time as you're migrating your stuff to the cloud, then you want to not only send the historical data, but also send new data as it arrives to your organization, send that to Amazon as well. So if you're interested in how this works, all right, they'll talk about it. You have some stuff. Why do we migrate? What happens? Da, 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 da. And you can poke around in here a little bit if you want. But anyway, good reading if you're interested in that. If you're an IDS major, you should probably know a little bit about cloud. That's the children downstairs. I don't know what they're screaming about, but I'm sure it's something trivial. You know, it's probably something like, you know, one of their eyelashes fell out. Now they're having an argument over who gets to eat it or something. Anyway, okay, next thing, comparing cloud vendors. Now, most of the time, if you go to cloud, you're going to save money versus doing it under your own roof. But the question is how much money and what features you have, how well it's going to work. So in most cases, businesses typically think of cloud, they think of it in terms of not, are we going to save money? Because they are. They think of it in terms of how well does this cloud model fit what we need? Does it have all the features we need? Because if we have to go through the headache of resetting all of, remigrating everything because this cloud service didn't have stuff we needed, it's not worth the hassle. So businesses tend to look at the features that are available and see if the cloud service fits them. Now, all this evaluation process is a difficult thing because most of the time when businesses have done it, they don't have a lot of experience with it. They, they don't know exactly what they need. They don't know exactly what the cloud offers, and they don't know exactly how much they need any of the different factors that are available. So simple example, right? So when I say here, intermittent problems tend to be wrongly weighted. Simple sampling error, okay? So imagine, suppose there's some problem that arises randomly in 10% cloud deployments. Okay, 10% of the time, this horrible train wreck of a problem is going to happen. Well, one way businesses might be aware of this, suppose the business looks at case studies or asks around. Okay, well, if they ask 10 other businesses, it's only about 50% likely that exactly one will see the problem. We'll see it. We'll have seen it. Okay? It's about, about 40% chance that no one has seen it, which means massively understate the problem, right? Nobody's seen it. And about 10% that more than one have seen it, which again, massively overstates the problem. And you multiply this estimation error by the number of potential problems, and you can see that a business might not make the best decisions, right? It's just hard to know. And it's hard to know because you don't get complete total data about everything, and businesses often just can't know it. So this is a problem. What else? Well, the very nature of cloud itself makes it a little bit hard to peek behind the curtain, right? So for example, you might be very concerned about cloud security, but how do you get that? How do you know how good the cloud security is? You can't just go in there and poke around and see, oh, this is how they do it. Okay, this is good. I mean, you might see some audit reports. They might have a good reputation that there haven't been any data hacks, but it's really hard, to have any certainty about how good the cloud security is. All right. So typical things you might look at as best you can assess them. Okay, this was a list that I lifted from some fellow's research paper several years ago that said, yeah, if we were going to look at cloud services, these are the sort of things we would want to look at. So first one, accountability. Is the cloud service frequently audited? Are they compliant with regulatory requirements? Do they follow best practices, that sort of thing? And who owns the data? Do I own the data, or does the cloud own the data? So an example of data ownership is Google Analytics. So we've talked about that in the web analytics bit. Basic Google Analytics, you don't own your data. Google does. So if something goes wrong, Google says, whoops, sorry, we lost your data, but you can't really sue us because it was never your data. We just let you peek at it. On the other hand, if you go with 360, the premium one, then you own the data. And if Google does something to lose your data, you can say, hey, you lost my data. I want some money for that. And Google will probably have to pay up. Second, agility. How easy is it to integrate new features? How fast does it happen? What are the elasticity bounds? So for example, if I want to switch overnight from going from one server to 100, is that possible? Is it possible to go from one server to 1,000? And is it possible to quickly snap back down from 1,000 to 1? Most of the big service providers, that's not really an issue, but some of the smaller ones, maybe. Cost, right? Cost is pretty straightforward. How much everything costs and how it's measured, right? In terms of data volume, how much data you're sending over the network or how much you're storing. If you're reserving machines, whether they're virtual or actual machines, how much different applications are going to cost if those are available as features in the system. So cost is pretty straightforward, and that's one of the easiest ones to measure. Guarantees. So service level agreement is basically a fancy term for a contract. The business specifies what service it will deliver, and if they fail to meet that obligation, then you can sue them for some, or get arbitration, whatever. You can get some sort of compensation. So typical things might be something like 99.99% uptime, and they're not going to lose your data, or they're going to keep 99.999999% of your data. And if something goes wrong, well, again, you can have recourse. And problem resolution generally, how is their customer service? Performance, again, performance is fairly easy to assess, like cost. Do your applications run well in the cloud once they're fully tested and you know, how well does it work? Then security. Security can't peek behind the curtain, but you can look at their security assessment results. So they get audited by outside operations, and they'll give them essentially a thumbs up or a thumbs down as far as their security. You can look at their history of data breaches, if any, and what sort of privacy is guaranteed, right? Typical thing there is how many other people are going to have access to the same hardware that your stuff is stored on. And last, usability. This one is going to vary widely across different businesses. If you have people that are already experienced with cloud, then their idea of usability is going to be quite different from someone who's a complete novice. But mostly these things are designed to be pretty easy to set up. For one of the graduate classes, when I was teaching IDS 520, I went on to Azure for the first time, Microsoft's cloud, and set up some back-end database there and a web interface with it. And it was, even though I'm old, it was pretty painless. I had it all up and running within half an hour, and it would have been a lot simpler. It would have been a lot sooner, except I missed one step in the instructions and I had to go dig around with that. So anyway, so most of these things, they're pretty easy if you have a technical background, but again, if you're a total novice to it, it might be a little weird. So, you know, some systems are more user-friendly than others. Okay. Last thing, cloud security. I think this is the last slide. No, we have one more after this. Okay. So one fact, take it as a fact, cloud security is better than most private information system security. But the problem is it's opaque. You can't look in and see how they do everything. It's also true cloud operations are not invulnerable against security threats. So one of the things we'll talk about is this multi-tenancy problem where you have multiple users storing their same data on the same hardware. And sometimes things are specified incorrectly and users can have access to other data. So with cloud, there is generally a reduced risk of security problems, but it's hard to know exactly how much of a risk. Now, there are specific cloud problems. Number one, encryption versus performance. If your data is encrypted, is that going to be a drag on how well your system runs? Number two, if data is leaking out, how can you monitor that? So it is a very difficult thing to do. You don't necessarily have full access to the cloud. The cloud is actually tracking the network. So you have to hope that they're doing a good job. Improper cloud configurations allowing other tenants access. So these were kind of famous, and there were some iCloud hacks about 10 years ago. Anyway, the basic thing is this. Suppose this is a server, and there are various slices of data on the server owned by various users. So he gets the red slice, he gets the orange slice, he gets the green slice, whatever. He gets the blue slice. And in principle, right, all users should only be able to access data in their own slice. But sometimes things go wrong. There are security gaps. And so what the bad guys could do is they could run some kind of query like this. I'll use purple and basically say, well, I'm supposed to only access this here, but you know what? I can run a query and capture data from this whole slice of everything on the server. And yeah, that was kind of messed up. So they could run that in a few different places and they'd get large swaths of data. Yeah, and they'd grab all of people's sensitive information, and who knows what horrible things they would do with it. All right. Anyway, last one, deletion assurances. So you guys know, if you get rid of an old desktop or an old laptop, one of the things you should do is basically destroy the hard drive. In some way, get all your data off of it. But with cloud, those deletion assurances, yeah, they're going to tell you they do it, right? If you're with Azure for 5 years and then you go say, yep, sorry, Microsoft, we're leaving, we're going to Amazon. And Microsoft's like, yep, okay, we'll delete your data. And you're like, I know. And they're like, what? And you're like, what? Yeah, you hope they delete your data, but you don't know for sure. You can't go in there and physically peek at the machines. And in fact, there have been occasional instances where data gets left on machines. So you guys have surely heard of Snapchat, where the images vanish, 30 seconds or so after they're posted. Well, In some cases, they have found that backup copies in the cloud, something went wrong with the deletion process, those backup copies stuck around for a while. So in that case, not a major thing for most people, but the point is you're never 100% sure that your data is all deleted. All right. Last thing to talk about, networking as a service, which might be the long-term future of cloud. So your basic models, you store data, you run application through the cloud, but you still have to manage the flow of data into your organization. With network as a service, you deploy your entire network to the cloud. This is what we talked about a little bit before with some of like Cisco's DNA. So let's draw a picture. Ordinary system, you and cloud. Okay, so you have some sort of connection between you and the cloud, some sort of routed connection I'll draw in red. The work is happening here, but all the data gets sent into some sort of routed channel, and it gets broken up through routers within your organization, and then it has to be sent over switch connections to the various machines in your network. So you still have to manage all of this traffic flow. In the networking as a service model, all of that stuff happens here, right? So all of your, basically, the equivalent features, all of this happens, pre-happens in the cloud. Right, I'm gonna draw like this chicken feet package. And then there's still a connection between your organization and the cloud, but all of this stuff, right, all of this stuff is bundled together in the appropriate way to meet your quality of service targets and is sent in packets so you don't have to reformat it once it gets into your organization. It's all getting there in the proper sequence and the way it's supposed to be so everybody can get the data they need. You still have to have some network hardware here so that everything tapping off of this gets delivered to the right place, but it's pre-set up so it gets delivered to you in the order and sequence and prioritization that you want it in. That's what networking as a service is. So again, if you're a business that fundamentally does not want to be in the networking business, you're a car manufacturer or a shoe designer, whatever, you don't really want to spend your time doing networking, this is great. You don't have to worry about it. You just plug the cables into the wall and let Cisco or some other operation do the work. So the advantages, a lot of these network management activities, they're automated, they happen for you, you don't have to worry about them, and the entire system happens in some common management framework off your premises. It becomes somebody else's problem. Now, a few years ago, it started coming around as a couple billion. It's been expected to grow about 50% a year for the next few years. We'll see what happens down the road, but yeah, this is probably one of the bigger trends that's hitting the world right now, because fundamentally, a lot of businesses do not want to be as involved with networking as they are. So typical outcome for networking as a service, you're not really going to save money on it in most cases. It's going to cost about the same, but your network is going to work better, and it's going to be a lot easier to manage. You don't have the headaches anymore. So you're spending the same amount of money, but it works better, and you can focus on other things in your business. All right. That is it. That is it for this cloud services chapter. Any questions on this stuff? Okay, so I'm going to stop the recording on this, and we got a second one. We're going to make a little dent in our transaction systems.